In the last part of this lecture, we have discussed mainly the demand of hydrogen, the actual status of production, and we also have discussed safety concepts. So 120 megatons of hydrogen are produced worldwide. Accidents occur, but very seldom, and this is mainly due to the fact that we handle hydrogen in closed industrial areas with experienced personnel. So if we have new processes, like we have seen on this slide, we want to use hydrogen everywhere, in households, in filling stations, in trains, and so on. We also need some new safety concepts here. For safer production, storage, and distribution in all these application sectors. And the problem is we need some more background for proper safety assessment. So an example here, we have large-scale explosions. So they have here these containers, classical 55 feet, no, 20 foot containers, filled with hydrogen and air mixture, and they ignited these mixtures inside these large structures. So it's something completely different to the small videos I have shown you, where we really look on specific small conditions. And of course the demand is how to numerically handle such a configuration. So if we would use a fine grid for a 20 foot container, we would yield in billions of grid points. So it's quite difficult to handle this numerically. So here, for example, you see the experiment. We have a pressure rise, and this will open, and then we have a reburning, a second pressure rise here. And after optimization of their numerical setup, they were able to see the same effect. But of course, you get totally different numbers here. So even though we have quite good numerical tools today for such large scale explosions, there is a lot of more research necessary to get sufficient agreement between numerical and experimental results, and we need these numerical tools for proper safety assessment. We cannot rely only on expensive experiments, and of course then one specific topic is here the DDT, deflagration to detonation transition. So here we have again only a deflagration, but if we would talk about a detonation, the consequences are much higher. So we have an idea to use hydrogen in transport sector is to use high pressure tanks. So typically 350 bar pressure, and other applications talk about 700 bar pressure in your tank.
Can you switch on your mic?
I will learn it until Friday. So when you have this hydrogen in high pressure tanks, the advantage is it's no longer an ideal gas, and you can store much more hydrogen at specific conditions compared to an ideal gas. So that's the advantage. So again, 700 bar is the aim for transport sector. So at the filling station, we talk about 1000 bar for a short time, and storage with 700 bar. And the question is, if you have such a tank and sudden release due to an accident. So you have a spontaneous outflow of hydrogen with very high pressure into an ambient atmosphere. And what we can see here on this sketch, of course, you have several effects. You have primary shocks, and you have Mach waves, and so on. So you have a strong interaction of the fluid with the hydrogen-air mixture here, and you can observe outer ignition. So the compression effects lead to temperature rise, leading finally to an ignition of these mixtures. So this is a well-examined problem, but nevertheless we need further model description or development for the description of these large-scale phenomena, especially the coupling of combustion with blast waves. There is still a lot of demand for research. But then also we have to do some work with material properties. So if we store hydrogen at 700 bar, there are several classifications, of course, but there's also a lot of work going on in this area. Then an idea is to use liquid hydrogen, which has a very low boiling point. And here you see a big experiment, leakage of liquid hydrogen and subsequent ignition. So giving this nice flame ball here. If we use the liquid hydrogen and we talk about really low temperatures here, we can have, for example, oxygen enrichment on the surface of the very cold pipe. So then we do not, in case of a leakage, just face with air. We have enriched oxygen here, which then of course supports ignition and combustion. We need to know the transient combustion properties of the cold premix systems. Some work is done here already, but of course it's quite expensive. So there's a big demand here. And again, we are talking about material properties. So when we have this very cold liquid hydrogen in contact with steel, with pipelines, with storage tanks and so on, of course there is a lot of work necessary here for proper solutions. So this is an image of my own PhD thesis, so I was happy that I found some space to put it here. So I've examined the flammability limit of here methanol air mixtures. And so we have here the explosive region, and here we have a region which are not combustible. And what we know from literature is that, or what is a simple assumption is that the flame temperature does not change along this connection line. So here we have the flammability of methanol in air. Here we have the flammability of methane in air. So if we have mixtures of these combustibles, the lower flammability limit does not, or does follow this simple line here. So, and when we assume this for the upper flammability limit, we see when we compare it with numerical work and with experiments, it looks totally different. You see a broadening of the explosive area here, and this is due to the fact that we have, of course, combustion kinetics here which are dominant. So the simple assumption that we have a constant flame temperature along the flammability limit does not work here. Here we have a methanol flame. Combustion is dominated by this combustible, and methane is more or less interacting only and burned later on. And this change here we have a pure methane flame. So the chemical kinetics change in this area. And of course, this is very important if we want to handle here with safety. And there's the same we see. So there is one idea. Okay, we use ammonia as a hydrogen carrier. And the big problem is how to crack ammonia. This is not finally solved. So maybe we can use it directly as a combustible. The big disadvantage is here that the ignition energy is quite high, the flame velocity is very slow. So there's the idea to have onboard cracking, for example, in cars, so that you enrich your ammonia with 10 or 20% of hydrogen. And you see here 20% of hydrogen, you strongly decrease the minimum ignition energy necessary for ignition. So this has a strong effect. But of course the problem is, okay, when we deal with ammonia, very high ignition energy, 14 millijoule, hydrogen, very low ignition energy, 17 microjoule. What about the mixtures? And is it only dominated by the ignition, or do we see some similar kinetic effects? So this we don't know at the moment. And of course, when we handle this mixtures, we need to learn a lot concerning the material properties to handle, to transport, to store this safely. So to deal with this topic at PTB, we want to build up an equipment you see here. So we start the investment now that we have a grid power source simulation together with an electrolyzer. The idea is, if you have your energy from renewable sources, you do not have a constant 50 Hertz electrical grid. You have fluctuations in your grid, and the question is, how does this influence the efficiency and safety of typical electrolyzers? Then we want to have gas purification and hydrogen storage here, and in this first step we want to use hydrogen only in the lab. But you also see here different other stages where we may invest in the future. So why do we want to do this at PTB? So you see here different quantities: flow, efficiency, process quantities, pressure, fluid properties, purity, and technical safety. And at all these different stages, we have to solve some fundamental problems. For example, if we talk about flow measurement with very large volumetric flow of hydrogen, so do we have proper measurement devices? Are they calibrated properly? This is one example. Or here, if we consider such an electrolyzer, what is with safety if there is a rupture of your diaphragma in the electrolyzer? So we have a pure hydrogen atmosphere, we have a pure oxygen atmosphere. So the worst case is directly existing here, and only some millimeters are responsible here for the safety. So we have a lot of research topics here, and the advantage of having such a structure, we can go to the limits. We cannot do this somewhere else, go to a company which is using such an electrolyzer and say them, okay, now we will try to start an explosion in your electrolyzer. I think this will not be possible. but this we can do here on our own. And you need a lot of metrology for green hydrogen. So first of all, the gas grid. When we consider the existing gas grid, where we have mainly methane, we want to add up to 20 to 30% of hydrogen to this gas grid. But we pay not for the amount of gas, we pay for the heat. So how can we measure then properly the heat when we have fluctuating mixture composition in our gas grid? This is of course very, very important for the economical characterization. Then, okay, safety technology we will have in the next session. Then we have a lot of quantities: pressure, temperature, flow, density, caloric value, purity, efficiency, where we need or where we have a large demand to learn more. Net caloric value, reference gas mixture, safety parameters, spectral data of importance. So when we talk about fuel cells, we need pure hydrogen. So 99.97% of hydrogen. So with only few other gases. How to measure these gases at these low concentrations? That's the first thing. And then, of course, how do these small trace gases then contribute to the energy production? So for what do we pay finally? And this is the green hydrogen value chain. So you produce electrical energy using renewable sources, and then in your electrolyzer you produce hydrogen, you transport this hydrogen, and finally you have the utilization at the end user. And along this whole chain we have to apply standards, we have to measure, we have to consider inspection, we have to consider testing, and we have to consider standardization and certification. Again, here, for example, the idea, okay, to replace this part with a coal plant and to sell green hydrogen here, but using fossil fuel for production of electricity. How can we identify this? How can we measure this? So we need, of course, then certification. So we pay for green hydrogen, and we need along this whole chain that this hydrogen was produced from renewable sources. And so there's a big demand here. So when we want to deal with hydrogen, we have new safety requirements, and we have to handle the problem that we have hazards along the whole hydrogen chain. From production to transport to storage to consumptions. The existing standards cover hydrogen completely at atmospheric conditions. So for liquid hydrogen, for example, there's a big demand for new standards. And of course, we need a great need for training so that we have proper engineers and technicians here who can work with this topic properly. For mixtures, we need to know much more about reaction kinetics. We need more safety characteristic data. We need more information about material properties to store and transport hydrogen properly, especially for liquid hydrogen. And when we have to improve our measurement devices for a lot of applications. So with this, I would like to end this session. And do you have questions?
Yeah, In the previous session, you told that
Yeah.
when the atmospheric hydrogen will reach 18%,
1/8.
18%,
Yeah.
then it will be flammable, or it will flammable in the atmospheric air itself.
Yeah. So I've shown it here on one slide,
Yes.
but this number was an error. So the lower explosion limit is 4%.
Okay.
Huh? And so what you mean is really possible?
Yeah. Is it really possible? Because now the percentage is 0.0005, I think, triple or quadruple 0.05%. Atmospheric hydrogen percentage.
So you mean the hydrogen in the surrounding atmosphere?
Yes.
Okay, now means if you have a leakage
Okay.
and a mixture of hydrogen with air.
Okay.
This mixture need to have an amount of a minimum 4%. Then you are in the explosive range. So it's not,
Okay.
of course, not the atmosphere we have.
Okay,
It's always in case of a leakage, an unwanted
Mm-hmm.
outflow of hydrogen, and this then mixes with air. And then you have a very broad explosion region from 4 to 78% hydrogen in air.
Okay, this how far this hydrogen research actually reached till date? So I just want to know, because for hydrogen the production part is not a bit of difficult, but the storage, transport, and handling is the major concern.
Mm-hmm.
So how far it has reached in terms of all those aspects, means storage, liquefaction, and transport. Because for the liquefaction it's needs around 30 to 33 Kelvin temperature.
Yeah.
And
So I'm not sure if we have time on Friday to discuss it further, but it is not decided yet. So of course there is some work. What is the most effective way to transport hydrogen over long distance when you consider costs? And when you, for example, produce hydrogen here in India and want to sell it in Germany,
okay.
you would transport it directly after liquefaction.
Mm-hmm.
So you cool it down to very low temperatures.
Mm-hmm.
But that means that you lose already 33% of your energy for this process. Then you put it on your ship around Africa or through the Suez Canal towards Europe. During the transport, you lose a lot of hydrogen too.
Oh.
Mm-hmm. So finally, you have huge losses when you use this way. So maybe it's better to use the Haber-Bosch process to get ammonia.
Okay.
You have some losses there too, but then you have ammonia, which you can handle much easier, which you can transport much easier.
Yeah, then to extract it from there.
Yeah. So there are solutions for both ways. So
Yes.
I think there is a tanker for liquid hydrogen going from Australia to Japan.
Yeah.
There were tankers already coming to Germany with green ammonia. There are ideas to produce green methane, so capture or store the carbon dioxide you have in your process, and then use green hydrogen plus carbon dioxide to have green methane at the end. But at the moment we have only ideas, so no
Okay.
large realizations.
Is the molecular weight is very low, so like other gases, as we transport them through the undersea pipes.
Mm-hmm.
Okay, so by addition of some powders or some other chemicals, so can we think of transporting this hydrogen through pipes?
Yeah, this is, for example, when you consider Tunisia, Mediterranean area, there is an existing pipe for natural gas from Northern Africa to Europe.
Yes.
So there is a concept to have green hydrogen and put it into this pipe. So for shorter distances, pipes are sufficient. But we cannot build a pipe from Australia to Germany, for example. So
Okay.
there we need other ways for transport. Okay, so the topic was carbon dioxide reduction. and we have focused now mainly on hydrogen. Depending on the time we have on Friday, we will continue this with other energy carriers. But this, of course, depends on the time we need, because I would like to start with application here. So we have learned a lot about theory, how to handle combustion, what we need to know, transport properties, chemical kinetics, and so on. And Professor Zahu will maybe explain the application of all these background with combustion engines or gas turbines. I would like to focus on another application for the rest of this lecture, and this is explosion protection. So we have two parts dealing more with the fundamentals, and two parts dealing with application. That means we will focus on a specific problem: flame transmission, flame arresters, flame-proof enclosures, and so on. So the propagation of flames through small holes, and the other thing is minimum ignition energy. So we always have only an energy value, but of course we have to consider the plasma formation, the initial heating of the gas volume, the onset of the chemical reaction, and finally the step to the self-sustaining flame propagation after ignition. So behind this number of 70 microjoule, there is a lot of chemistry and physics which we have to consider. This I will discuss later on. But first we need some combustion fundamentals, because I've seen with this hydrogen lecture there were maybe some question marks: MESG value, MIE. What is this? How do we need it? So with the onset of the industrialization, the demand of energy has increased drastically. So first we use steam engines with wood and then with coal, and so we dig deeper and deeper for coal, and unfortunately we cannot find only coal below the surface. In this coal we also can find methane pockets, and so there were a lot of disasters in coal mining. Here just a plot from the US. So around 1900 something, still we have had a lot of accidents with a lot of fatalities. So here it's nearly 12,000 people have died in coal mining only in the US in this period here. But what you also can see is that the occurrence has decreased drastically. So there are still accidents are occurring, and still people die in mining areas, but of course this has reduced drastically. So we have a lot of new safety concepts here. We know much more about the safety requirements, but still we have to improve here. We are not at zero. Another example is here this well-known Deepwater Horizon accident. So in oil and gas industry, where we deal with fossil fuel, a lot of accidents occur, and sometimes they have such drastic consequences here. And it's not only the case that some people died here, and the investment for this oil rig was quite expensive. There was of course a leakage of large amount of oil, so a subsequent pollution of the sea here in this area, which has had heavy consequences. So the cost of such an accident is a range of billion of euro or dollars. Another example here, this Buncefield fire. So here, this was in tank depot, storage of combustibles, mainly for Heathrow Airport, and so here a big accident has occurred, and you see this smoke plume. There was fear that this reached London area and so on. So they have had several measures to avoid here any consequences, but nevertheless we talk about billions of euro here too. There's an example here, Texas City refinery explosion. So here in this area there were some temporary buildings where people are working. So I don't know the number of fatalities, but several people died here after an unwanted release of combustible. But also sugar dust here as an example is dangerous. So when you deal with dust, we will have a special focus on this. Of course, drastic consequences can occur. Here we have the same with grain dust, which quite often occurs. So the consequences of such an explosion can be quite drastic. So when we deal with explosion protection, we need some definitions. We talk about gases and vapor explosions. We'll talk a little bit about dust explosions. And I just mentioned hybrid mixtures. Hybrid mixtures means in this case mixtures of flammable gases and flammable dusts, which the safety aspects are quite difficult to handle. So to show you an example how we deal with this in Germany, this is maybe not the correct example, but so in summertime we often have some article in the newspaper that someone has his grill and started the fire with gasoline. And then we will see it here in this video, they do it too. It can have heavy consequences, so he's using gasoline to ignite finally the wood here. And so he is a clever man, so he is making try to ignite it in some distance. Okay, here we have some rest of gasoline. It will help, of course, for burning. So everything is empty, and now with some safety distance he will ignite the system. But he has not realized that, of course, gasoline has a high vapor pressure, so he was in an atmosphere of gasoline and air. And he has not ignited this liquid hydrogen. He has ignited the rest. But okay, he has survived it, but it not always is as positive. So we have, as I've said, a lot of accidents when people try to ignite their grill using gasoline. But so he was only a short time at 2000 Kelvin, so he survived it properly. So when we want to deal with flammable gases, vapors, liquids, and dust, we need to consider a lot of topics. So first of all, an explosion is a sudden increase in volume and release of energy in an extreme manner. So of course you have your classical explosion engines, your combustion engines in a car. It's also an explosion. There you take advantage of the concept, but here we talk about unwanted explosions, and we have nuclear explosions, physical explosions, which are not in the focus of this lecture, but we talk about chemical explosions, so spontaneous exothermic oxidation reaction accompanied by a sharp rise in pressure and temperature. We have deflagrations with quite low flame velocities. So here we have a flame propagation mainly due to conduction and to diffusion effects together with convection. So the flame velocity is in the range of 10 to 500 meters per second, and the maximum pressure is 10 times the initial pressure. So much more severe are detonations, so we have much higher flame velocities, and we yield much higher explosion pressures. We can have jet flames, so when you have, for example, a leakage at a pipeline and you ignite the gas jet coming out of this pipeline, you will have such a jet flame. And blabbies, boiling liquid expander vapor explosions, you could look for this at YouTube. Typical accident, you have a tanker filled with gasoline, and then you have a fire below this tanker. So you heat up the gasoline, it starts to boil, and it's a closed tank, so the pressure increases. Suddenly there's a rupture, and this then expanding vapor cloud comes in contact to the fire. You have suddenly a spontaneous release of a large amount of combustible, leading to a very impressive flame ball. And of course, a lot of severe accidents have happened in such a case. So, okay, this we have discussed already with the last slide. We need proper amount of combustible, oxygen, and ignition source to start an ignition. Normally, there are some gases like acetylene, where you not always need an ignition source, but here we do not want to focus on these problems. So we have to consider spread of gases. So here with hydrogen, we have seen hydrogen, methane are lighter than air. So if there's leakage, these gases will go up. But most hydrocarbons we have are heavier than air, so they will go down. And this, of course, is a problem when you have something like this. So your combustible can go into areas where you do not expect it. So you have to take care of this. And here, for example, we have ventilation as a concept to avoid an explosive atmosphere here. But of course, we have to consider that we may have an explosive atmosphere there. So you always have to consider here the spread of gases. Also with liquids, this can occur. So if you have a leakage, of course, they will always go to the lowest point. And there were accidents, for example, in Mexico. There was a leakage at a petrol station. It went to the local sewer system, spread all over the city, found an ignition source, and then nearly half of the city was destroyed afterwards. So you have to take care, of course, if you deal with combustible liquids. Therefore, we have normally special measures. And you have to consider that 5 milliliter of gasoline, so which is very small amount. So this small cup here produced enough explosive atmosphere in such a 200-liter vessel to have an explosive atmosphere. And so there are still accidents, so people should handle with these empty barrels, and for example, to open them with a flex, with a grinding machine. So you look inside, oh, it's empty, no liquid inside. Okay, they sit on this barrel and then they use a grinding machine here. And they have inside this explosive atmosphere. So it's of course not healthy when you do this. So you have to consider this. You don't see any liquid inside, but you can of course have an explosive atmosphere. And here you see an expensive Porsche after an fire, and the reason for this fire that there was some small amount of brake cleaner, combustible brake cleaner, finally leading to this fire. So again, we start with a very small accident, but the outcome could be catastrophic. The same we have with dusts. So of course we normally have dust layers, so they are heavier than air, but we will see it. So dusts take some time before they go down. So for example, if you want to clean it, you should use proper vacuum cleaners and not this method here, because of course you produce an explosive atmosphere. So when we talk about avoidance of explosive atmosphere, so that's the best and simplest method. If we don't have a hazardous atmosphere, no explosion can occur. So indoor we use natural ventilation, forced ventilation, but also you can use proper gas sensors in your lab. I don't know, do you have gas sensors in your lab where you deal with combustibles? You have dealt mainly with liquids, but later you have dealt also with biogas, right? Yeah, so in Germany, when we deal with combustible gases, it's mandatory to have gas sensors. So we have normally one for the heavy gases, and when we deal with hydrogen, methane, one for the lower gases. So one near the ground and one near the top of the building. So, and these gas sensors then realize quite below the lower explosion limit there is a leakage of whatever, and they give a warning, and after this, if there's still an increase visible, they shut down the whole lab, for example. So all the electricity and so will shut down, and everyone has had hopefully enough time to leave the area, and firefighters can come and check. So outdoor, okay, avoidance of combustibles, that means substitution. So use substances and so here liquids with higher boiling points. Avoidance of combustibles also means always be below the lower flammability or explosion limit. So this we will see later more in detail. You can use padding gases, inert gases like carbon dioxide and nitrogen. And you can try to stay above the upper flammability limit, which was a concept, for example, for tank ships in Germany for a long time, because we now have a closed system. So you fill a tank on land with the oil or gasoline from your ship, and then the atmosphere from the tank is going to your ship tank, so that there is no leakage of hydrocarbons to the outer atmospheres. So inside your ship tank there is now no liquid anymore, but a very rich mixture of combustible in air above the upper explosion limit, so it cannot burn. Safe concept until you have an accident. Your ship hits another ship, there is a leakage, then release of your combustible. You find a proper explosion mixture, you have an ignition source, and you will have a fire or explosion. Everything has happened So it's a concept, but of course you have then to take care. So, okay, safety characteristic data we have discussed already in the last lecture. These data we need because we have thousands, maybe millions of combustibles to consider. And we do not want to have safety concepts for each of these combustibles, but we need to know how easy these combustibles will ignite, how fast they burn, and so on, to have proper measures to avoid any consequences. So as I've said before, we don't have material constants here, so it depends strongly on the determination method, but it gives us quantitative information about the material properties. So 40 millijoule minimum ignition energy of ammonia means it has nearly 1,000 times higher ignition energy compared to hydrogen. So ammonia we can handle much easier than hydrogen. Therefore we need this data. And we have a long list here. So quantifying explosive mixtures, we talk about explosion or flammability limits. We have the so-called flash point. We can quantify the ignitability, so auto ignition temperature, maximum experimental safe gap, minimum ignition energy, and minimum ignition current. These are typical quantities here. And we have quantities to quantify the effects of an explosion. So maximum explosion pressure, maximum explosion pressure rise. And with this, I would like to continue in the next session. So I would like to close for today, but first of all, okay, thank you.